auspicious day, we all have gathered here to organize an international webinar on mathematics and mathematical science. We feel very happy and proud for the presence of the renowned speakers, Professor Ravi P. Agarwal from Texas A&M University, Kingsville, and Professor Pat Muldowney from the University of UlsterNorth, Ireland, UK, who will enrich us with their wisdom and knowledge. Our webinar is being streamed on two internet platforms, on Cisco WebEx meeting platform, where the speakers and administrator of the meeting are present, and YouTube platform where the whole world can see this webinar. Our participants will also be present in that platform. I hope all participants present here will help us to complete this webinar successfully. Now we start the inaugural session. Firstly, I would like to request to Swami Vedanuragnanda Maharaj, Controller of Examination of Ramakrishna Mission Vivekananda Centenary College, for a short welcome address. Please start, Maharaj.
Good evening, everyone. Welcome you all to today's international webinar organized by Ramakrishna Mission Vivekananda Centenary College, Rahara, Kolkata in India. We are very happy to organize this webinar on mathematics and mathematical sciences by the Department of Mathematics of this college. We are very glad and feel ourselves fortunate to have Professor Ravi P. Agarwal from Texas A&M University-Kingsville, who will be speaking on the topic, "Are we prepared to accept the reality?" And another eminent speaker is Professor Pat Muldowney, University of Ulster, Northern Ireland, North Ireland, UK. We are very happy to have both of you, sir, and we welcome you on behalf of the college and on behalf of all the organizers of this webinar. We are also very happy to have Professor P.C. Pal, retired Professor of IIT Dhanbad, West Bengal, in IIT Dhanbad, India, as the chairperson, and Professor D.K. Ganguly, retired Professor of Calcutta University and Vice President of Calcutta Mathematical Society, West Bengal, India, as the chairpersons of the two sessions, where we have these two eminent speakers, Professor Ravi P. Agarwal and Professor Pat Muldowney. So, on behalf of the college, I extend a warm welcome to all the speakers, chairpersons, and all those who are participating in this international webinar. The Ramakrishna Mission Vivekananda Centenary College is an integral part of the Ramakrishna Mission worldwide organization started by Swami Vivekananda. And Swami Vivekananda was always for a wonderful harmony between science and spirituality. So we have a rich heritage where science, service, and spirituality are blended in one system for the betterment of mankind, for the upliftment of mankind, and so that man grows from within as well as in all dimensions. So with this brief background, I welcome all the speakers and participants to this webinar and hope that it will be enriching, and all the speakers are quite renowned with their long experience and their wonderful wisdom. We will definitely be enriched by their talk, and we hope that in now and again in future, whenever possible, we'll try to get access to their wisdom and knowledge so that we can grow and develop in our fields. Thank you, sir, for attending all these webinars, and I welcome all. With these few words, I would end my welcome address.
Thank you, Maharaj. Thank you. Next, I would like to request to Mr. Maharaj, Swami Kamalasananda, Ramakrishna Mission Vivekananda Centenary College, for an inaugural speech. Please start, Maharaj.
So, we are very happy to be in this international webinar in mathematics and mathematical science. And here two very respected, prominent figure, experienced teacher like Professor Agarwal and Professor Muldowney. Both are the resource persons this international webinar. And this type of webinar, every year we organized in our college through our various departments. Just before this COVID-19 situation, we always organize this type of national and international webinar in offline mode, where all the speakers, they have to come to our college and they deliver their talk, and also participants from different corners of India and outside also come and join this workshop or seminar. But this COVID-19 situation gives the new normality, new standard of life. So there all the participants and resource persons, speakers, all the chairpersons, all are sitting their own place and listening and enjoying the proceedings. So this type of online platform we have practiced last few months. But before that, this type of national and international seminar we organized through our various departments of this Ramakrishna Mission Vivekananda Centenary College. And this college, I just tell you before that this college established 1963, the birth centenary year of great Swami Vivekananda, the philosopher and thinker of India. And this is actually the 1963, the birth centenary year of Swami Vivekananda, because he was born 1863. And from the very beginning, this college actually as a center of science learning and teaching, and also the higher field of a higher education field, and also the research and innovation field for science and technology. So through the various science department of our college, now actually this college is a very important learning center in India, because it already accredited by National Assessment and Accreditation Council of India and got the highest grade A. It is also an autonomous college, also conferred by University Grant Commission of India, and it is also the college with potential with excellence, also awarded by the University Grant Commission, and also so many this recognition by Department of Science and Technology. I mentioned 1 and 2, that is DST Feast, DST 0, that is Scientific Industrial Research Organization, and Department of Biotechnology also giving this DBT Star College. So these are the actually this milestone which indicates that college actually last more than 55 years it actually nurturing the higher education and the science and technology in a innovative and a very prospective way. And our students are coming from very rural area. They are coming from very marginalized family, and their families are very low income group. But after that, they are actually passed out from this college with a fine color, and they are spread all over India. Not only India, some students also they are doing their postgraduate degree, and some also faculty members of the different university of all over the globe. So in this background, we are very happy that have the Professor Agarwal and our Professor Muldowney, and both their topics are very, very interesting. That is mathematics and mathematical science. And I every time tell that mathematics is not a subject, it is a concept. So mathematics, but we have to study, so we have to put a that named that it is a subject. But mathematics is a concept. Without the concept, we cannot express, we cannot feel, we can touch, we can express our feelings, express our sense organ. So mathematics is a concept. So in this concept, our very important terms is mathematics and its reality. And this mathematical reality has come, but it has very, very practical application. I see that suppose I tell that our Professor Agarwal or Professor Muldowney is a very good student at the student life, and they are a very good teacher. They have many publications, more than 3,300 or 1,000. They have written many books. These are the statements. And at the same time, I tell that we are very happy to have Professor Agarwal and Professor Muldowney in this webinar. These two statements I am telling, these two statements are true, but both are related. Previously, I told that Professor Agarwal or Professor Muldowney, they are very good students. They are very good teacher, more than 45 years experience, and they have many publications. This quantification, this type of analysis, these things gives the mathematical one part, mathematical reality one part, that is called the practical aspect of mathematical reality. But we at the same time I tell that we are very happy to have Professor Agarwal and Professor Muldowney. This this mathematical reality relates this happiness of ours with this previous qualification. But more than this, this relation, we also actually express our happiness beyond this, because happiness could not only depends upon that they are good student, they are good teacher, they have published many articles, but something beyond we could not express now. So these things we call that theoretical aspect of mathematical reality. So this mathematical reality, mathematics and mathematical reality, it has two aspects, practical aspect and theoretical aspect. And this practical aspect and theoretical aspect both are dependent upon time, space, and causation, and highly related. So what I could not express that why we are happy. Maybe tomorrow or after 5 hours we can immediately quantify that we are happy for so and so, so and so, so and so reason. So this mathematics and reality and its theory and practical aspect is a very, very important terms in our day-to-day experience. And our actually India in previous time, those have come, they are very much profound in the theoretical aspect of this mathematical reality. And maybe I think Professor Agarwal will highlight this. And our Professor Muldowney, he has dealt with very important topic, that is the mathematical basis of Feynman diagram. This Feynman, Professor Feynman, is highly efficient correlating the subatomic particle, that is this positron and electron, how collide and annihilate, gives photon, and from this gives this quark, antiquark, antiquarks gives gluon. These things very simplified way, he gives a diagrammatic representation. This diagrammatic two-dimensional or we can three-dimensional representation means that it is a quantification of mathematics. So we quantify this from a whole very abstruse concept in a very lucid manner, that how this relate from this positron to electron to photon to quark, antiquark to gluon, all this. So this quantification is also the practical aspect of mathematical reality. But we know that beyond gluon something is there. And we also know that electron and positron also would not produce nothing. It also produced something. So this something and beyond gluon also both are present. But at present we could not express it. So it is the theoretical aspects of mathematical reality. So these two topics we are somehow accidentally we framed, but these two topics are highly related in this webinar. So I think we are very lucky to enjoy their talks. So I do not extend my talks further. So let us join their talk and enjoy their deliberation. So thanks all of you. I express my regards and also my hearty greetings to Professor Agarwal and Professor Muldowney for their consent to deliver this their beautiful talks in this webinar. So thanks all of you. Thank you.
Thank you, our Principal Maharaj, for his inaugural speech. Now we have reached to the end of the inaugural session. Before starting the first lecture, I would like to tell some words introducing Professor Ravi P. Agarwal. Actually, Dr. Ravi P. Agarwal was born in Murshidabad on 10th July 1947. In 1973, he earned his PhD degree IIT Madras, India. His major research interests are on national numerical analysis, differential and difference equation, inequalities, and fixed point theorems. He has published 44 research monographies and more than 1,700 publications in prestigious mathematics journals. Dr. Agarwal had worked previously either as a regular faculty or as a visiting professor and scientist in universities in several countries. He has held several positions including visiting professor, visiting scientist, and professor at various universities in different parts of the world. He was awarded Most Respected Alexander von Humboldt Foundation Fellowship to work with Professor Dr. G. Hermelin at the Ludwig Maximilian Universität Malchen, Germany during 1981 to 82. His work is cited more than 15,500 times by 6,000 scientists. Dr. Agarwal is the recipient of several notable honors and awards, including Dr. Honoris Causa and many others. He was also nominated as a possible candidate for a BBVA Foundation Frontiers of Knowledge Award. Many BBVA award winners are Nobel laureates. Dr. Agarwal provided significant service to Texas A&M University, Kingsville. Under his leadership during 2011 to 19, Department of Mathematics consistently progressed in education and preparation of students and in the new direction of research. His overall impact to the university is considerable. Now I would like to request Professor Dilip Kumar Ganguly, Professor of Pure Mathematics, Calcutta University, chairperson of this webinar, proceed this session of first lecturer. Sir, proceed this.
Should I start? John.
You start.
Hello. Should I start?
Yes, yes.
Okay. Now we start our first lecture in this webinar. Our first speaker, Professor R.P. Agarwal, is a renowned mathematician that was introduced by our Professor P.K. Rana. Now his topic is very interesting. Are we prepared to accept the reality? So I request Professor Agarwal to deliver his lecture, but his duration of the lecture is 1 hour. So please, Professor Agarwal.
Good morning, good afternoon, and good evening to all of you. For me, I have not taken the breakfast yet. Anyway, first time I went to Calcutta was in 1974 to see Swami Ramakrishna Mission and particularly the Dakshineshwar temple. And it so happened that I met my wife there. We married within 7 days, and we are living happily from last 45 years. So that is the gift from Swamiji to me. Actually, the title of my talk, Are We Prepared to Accept the Reality, is actually dealing with the history, not about the mathematics at all today. I realized over the period of almost 50 years that the books written in the history of mathematics are written by Europeans, and they have written the history of Europe. They didn't bother to see what was existing in other parts of the world. So, can I have the next slide, please? Can you please move the next slide?
Next slide, Rana sir, next slide.
Yes. Yes. So, this is what is my claim, that rather I have written the abstract. In this lecture, an attempt is being made to convince the world, especially B Indians, that is really, in reality, Bharat, the greater India, is the origin of mathematics. This will correct the most of the historians of mathematics have claimed in their books, and we have accepted it religiously. We will also try to reassure that mathematics as well as proof cannot be defined. I will prove that the proof cannot be defined. Further, we shall discuss features of upapatis. This is a particular word originated in Pali, Sanskrit, and Marathi in Indian mathematics. So let us go to the next one. Let me start with a very, very prestigious book, and I will advise that every mathematician should read this book. It is by Vibhuti Bhushan Datta. It was written in 1932, The Science of the Sulvas, a study in early Hindu geometry. And it was from Calcutta University Press, Calcutta. Let us see what is written on page number 27. The reference to the sacrificial altars and their construction is found as early as Rig Veda, Samahita, and he has written before 3000 BC. It seems that the problem of squaring of the circle and the theorem of the square of hypotenuse are as old in India as the time of Rig Veda. They might be older still. Okay, just keep this one in mind. Let me continue. 4 Vedas, the meaning is knowledge or vision. Rig Veda, Sam Veda, Yajur Veda, and Atharva Veda were codified. These Vedas are existing right from the beginning of this earth. But these Vedas were codified by Krishna Dvaipayane or sage Ved Vyasa, and he was born in 3374 BC. Along with his disciples Jaimani, Pailya, Sumantho, and Vaishpayana. Each Veda consists of 4 parts: the Samahitas, hymns, There are Brahmanas, rituals, Aranyankas, theologies, and Upanishad, that is philosophies. Next. Arthur Schopenhauer, one of the greatest German philosopher and writer, he writes, in the whole world, there is no study so beneficial and so elevating as the Upanishads. It has been the solace of my life, and it will be solace of my death. They are the product of the highest wisdom. Vedas are the most rewarding and the most elevating book which can be possible in the world. As far as Vedas are concerned, nothing has been added and nothing has been deleted. Nothing has been contradicted. Everything, every word written in Vedas has turned out to be over the period of time that everything is true. Niels Bohr, Nobel laureate in 1922 for his theory of atomic structure, he writes, I go into Upanishads to ask questions. Now, I will suggest if you want to know more about Vedas, there are two books by Stephen Knapp. The Secret Teaching of Vedas. It was published in Bombay in 1993, but its earlier version was published here in USA. The second one, Proof of Vedic Culture's Global Existence, paperback. It is still published in USA in 2009. He gives hundreds of examples where you can see that the several things which are existing in the world, the origin of these ones has come actually from India. It is up to this extent that according to Vedic literature, or rather according to Hindu philosophy, the first creation was Manu. And in English, the word man has come from Manu. So one should read these two books and you will find that something is really, really interesting. During Vedic period, at least 5,000 years ago, it was known that distances of the moon and sun from the earth are 108, which is a sacred number in several Eastern religious and cults. I am sure you must have heard in front of many swamis the number 108. Now, why this number 108 has come, you must go to maybe to internet and you will find its importance. So I'll read again. It was known that the distances of the moon and sun from the earth are 108 times the diameters of these heavenly bodies. So these sun and earth are called heavenly bodies. The observed values are 110.6 for the moon and 107.6 for the sun. So whatever our rishis predicted 5,000 years back, without any instruments, without just the in samadhi state, whatever they observed or whatever came to their mind, that has turned out to be true. Hindus also discovered what is known as the precession of equinoxes, and their calculations such as occurrence takes place every 25,827 years. Our modern science, after labors of hundreds of years, has simply proved that to be correct. Not a single year has been added. This number was known, once again, almost 5,000 years back. Now let us see Jean-Sylvain Vallée, what he writes. He was great French astronomer and politician. he noted for his computation of an orbit for Halley's comet, the motion of the stars calculated by the Hindus before some 4,500 years vary not even a single minute from the modern tables of Cassini and Mayer. Let us see what John Wheeler has written, eminent American physicist, the first one to be involved in the theoretical development of the atomic bomb and the first to coin the term black hole, who later occupies the chair that was held by Einstein. He says, I like to think that someone will trace how the deepest thinking of India made its way to Greece. Please note this one. I think that someone will trace how the deepest thinking of India made its way to Greece, and from there to philosophy of our times. Next slide, please. The meaning of the word sulb is to measure, and geometry in ancient India came to be known by the name Sulva or Sulba. The Sulba Sutras are the appendices to 4 Vedas. Only 7 Sulba Sutras are extant, named for the sages who wrote them. So there are 7 names here. Only for Bodhayana, it is known that he was born in 3200 BC. Of course, if you will go to internet, you will find that these dates have been artificially killed. You will find that the date of birth of Bodhayana is written about 800 BC, but the actually birth is he was born in 3200 BC. The 4 major Sulba Sutras, which are mathematically the most significant, are those composed by Bodhayana, Manava, Apasthamba, and Katyayana. These Sulba Sutras contain a large number of geometrical constructions for squares, rectangles, parallelograms, and trapezia. The problem of solving quadratic equations of the form ax squared plus bx plus c is equal to 0, several examples of arithmetic and geometrical progressions, a method for dividing a segment into 7 equal parts. I cannot believe I struggle to divide a line to three equal parts. How they were able to do dividing the segment into 7 equal parts, solutions of first degree indeterminate equations, and without any proof. I am writing here very carefully, without any proof. Remarkable approximations of square root 2 and pi. Next page, please. Now, this is something very, very important. In the book, India in Greece, published in 1852 in England by Greek historian Edward Pocock, reports that Pythagoras, who taught Buddhist philosophy, was a great missionary. His name indicates his office and position. Pythagoras in English is equivalent to Pythagoras in Greek and Buddhagoras in Sanskrit, which implies that he was a Buddhist spiritual leader. See the way he used to teach, the way he used to handle his students. You will find that there is a similarity between the way it used to be in India and the way he was doing it. Now here, something once again very important. Note that Lord Gautam Buddha was during 1887 207 BC. Historians have misled the world by claiming that he flourished around 450 BC. So this is important. Now let us see Francis Voltaire, not the same mathematician, but he was one of the greatest French writers and philosophers. He writes, I am convinced that everything has come down to us from the banks of Ganga. He does not write Ganges, he writes Ganga. Astronomy, astrology, and spiritualism. Pythagoras went from Samos to Ganga 2600 years ago to learn geometry. He would not have undertaken this journey had the reputation of the Indian science had not been established before. Please note this one very, very carefully. This was supported by the same statement supported by Thomas Eliot. He was American-British poet, Nobel laureate, 1948. He has repeated almost whatever Voltaire has said. I am convinced that everything has come down to us from the banks of Ganga. Astronomy, astrology, spiritualism, etc. It is very important to note that some 2,500 years ago, at the least, Pythagoras went from Samos to Ganga to learn geometry, but he would certainly not have undertaken such a strange journey had the reputation of Brahmins since not long established in Europe. So this is important that nowhere in the books it is mentioned. They only say that he went to Egypt and he went to Babylonia, but nowhere it is mentioned. There is a Chinese, there is a book with the title that Pythagoras was a Chinese. Okay, so perhaps if you see from Buddhism point of view, then they are right, because his way of teaching was same as Buddhism. Next slide, please. According to historians, Pythagoras also went to Egypt and Babylonia in search of knowledge. Some prominent historians of mathematics, for example, van der Waerden and Stronik and Thomas Heath, have suggested that Egyptians had no knowledge of Pythagorean theorem. Once again, I contradict here, which is not true. See Berlin Papyrus 6619 and Cairo Mathematical Papyrus, unearthed in 1938 and first examined in 1962. Of course, there is a sufficient evidence that Pythagoras' theorem was known to Mesopotamian CY BC 72989 and Plimpton 322, written between 1790 and 1750 BC. However, above two quotations strongly suggest that Pythagoras learned about Pythagorean theorem and triples probably in India. I am using the word probably because nobody can be sure. For their origin, for the origin of Pythagoras theorem and Pythagoras triples. Patterns, extensions, astonishing directions, and open problems. I just wrote two papers. Both of these papers have just appeared a few weeks back. So I will suggest, if you want to see the origin of Pythagorean theorem and its generalizations and Pythagorean triples, you should see these two papers. These are popular papers. These are not research papers. Next page, yes. Now let us see, India is considered the land of numbers. She has produced several leading number theorists, such as Srinivasa Ramanujan. He became the Fellow of Royal Society in 1918. One should read The Person Who Knew Infinity. You will see what a tragedy, and particularly I will say that one should thank G.H. Hardy, who realized his talent. He was one of the greatest intuitionalists in the world, although this is once again very important, in the world, although there are about 4,000 languages, of which several hundred are widespread. There are only several dozen alphabets and writing systems that represent them. However, we can safely say that there is one single place value system that uses 0 and 9 numerals, symbolically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, by which any number can be expressed and understood rather easily. Now, by this sentence is very powerful. This gift of India has truly united the universe in the language of numbers. It is worth noting that there is hardly any aspect of our life in which numbers do not play a significant, though generally hidden part. Next page, please. Now let us see in 1875, sorry, George Thibaut translated a large portion of the Sutras, which showed that the Indian priest possessed significant mathematical knowledge. Thibaut was a Sanskrit scholar, and his principal objective was to make the mathematical knowledge of the Vedic Indians available to the learned world. He firmly believed that, please see this carefully, he firmly believed that Hindus had knowledge of irrationality, in particular of square root 2. In fact, in Apasthamba, there is a discussion of the irrationality of pi. So it is not true that irrationality was discovered by Pythagoras. Actually, in history books, you will read that everything started from Greece. But this is not true. It has been glorified so much that we cannot think beyond what was existing in the world before Greece. Now let us see Acharya Charak and Acharya Sudhrud. This was 600 BC. Charak has been crowned the father of medicine. His Charak Samhita is considered to be an encyclopedia of Ayurveda, which means science of life. In this work, there is also an interest in permutation and combination. His treatise, Swahar Samhita, states that 63 combinations can be made out of 6 different rasa. Rasa is taste. So, bitter, sour, salty, sweet, hot, etc. by taking the rasa 1 at a time, 2 at a time, 3 at a time, and so on. This solution of 63 combinations can be checked, 6C1 plus 6C2 plus 6C3 and so on. It turns out to be exactly 63. So I will say that the beginning of permutation and combination started earlier. Let us see Pingala. He was about 500 BC. He was the author of Chanda Shastra, the Sanskrit book on meters and long syllables. Pingala was the younger brother of great grammarian Panini, the author of the famous treatise, it is difficult to read Sanskrit name, Ashadhyay, of the 5th century BC. Pingala presented the first known description of a binary number system. Binary number system was used 500 BC. He described the binary number system in connection with listing the Vedic meters with short and long syllabi. His work also contains the basic ideas of Sanskrit names I will just ignore, but it means Fibonacci numbers and Pascal's triangle. So please note that Fibonacci numbers and Pascal triangles were known 500 BC. His book Chandra Shastra contains the first known use of zero, indicated by a dot. In his book, he also explored the relationship between combinatorics and musical theory. The credit goes to Pythagoras, that he saw actually numbers in musical theory, which was later reproduced by Mersenne. Around the end of the 10th century, Halayudha, about 975, produced a commentary on Pingala's Chandra Shastra, in which he introduced a pictorial representation of different combinations of sounds, enabling them to be read off directly. Halayudha's Meruprastara or pyramidal arrangement provides the binomial expansion of a plus b to the power n. That means binomial expansion was known 975. Now everybody has heard the name of Laplace, the French greatest mathematician, philosopher, and astronomer. Let us see what he has written about the numbers. It is India that gave us the ingenious method of expressing all numbers by 10 symbols, each receiving a value of position as well as an absolute value. A profound and important idea which appears so simple to us now that we ignore its true merit. Let us see what Einstein has written. Of course, he got his Nobel laureate 1921-22. He writes, "We owe a lot to Indians who taught us how to count, without which no worthwhile scientific discovery could have been made." Next slide, please. Underwood, let us see what he writes. He was French. He fell in love with mathematics and Sanskrit literature. By the age of 16, he had read Bhagavad Gita in the original Sanskrit, wrote in 1884. Let us see what he wrote. What would have been Fermat's astonishment if some missionary just back from India had told him that his problem had been successfully tackled by native mathematicians almost 6 centuries earlier. Fermat is considered as the father of number theory, and we see here that some of his problems were solved already 600 years before. Brahmagupta, born 30 BC, and Bhaskara II, working 486, had addressed themselves to some of Fermat's problems long before they were thought of in the best, and had solved them thoroughly. They have not had a proper place in mathematical history or received credit for their problems and methods of solution. So how much injustice has been done? Ancient astronomical tests such as Surya Siddhanta and its commentaries contains lot of trigonometric formulas. I have listed here 3 formulas. Bhaskara 1, before 123 BC, gave the following point-wise approximation formula for sin x, which has a relative error less than 1.9%. So point-wise, it is not uniform, it is point-wise approximation. How he obtained, there is a lot of discussion about this. Brahmi Hira gave trigonometric formula. Sin x is cosine pi over 2 minus x, sine square x plus cosine square x 1. So you can see that it was 123 BC. Now these formulas are known, particularly sine square x plus cosine square x is equal to 1 is known as Pythagorean relation. And the formula 1 minus cosine 2x over 2 is sine square x. Bhaskara 2 developed spherical trigonometry systematically and discovered many trigonometric results such as addition formula sine a plus b and sine a plus minus b. Next slide, please. Important exact formula for finding the area A of triangle having sides ABC, known in the literature as Heron's formula, was stated earlier by Bhaskara 1. So it was much before Heron it was known. A as a square root s, s minus a, s minus b, s minus c. The formula was later generalized by Brahmagupta for finding the area A of cyclic quadrilateral, given its 4 sides ABCD, and it is given by A is equal to square root s minus a, s minus b, s minus c, s minus d. Today this formula is known as Snell's formula, which was known in India almost 1600 years before. Next slide, please. Now let us see about the tangent, the term rather about the calculus. The term tangent was coined by Leibniz in 1684, which has been credited solely to Newton and Leibniz. For Newton, the calculus was geometrical, while Leibniz took it toward analysis. If you read the controversy between Newton and Leibniz, who introduced calculus, and the type of feedback he got from the Royal Society, you will be shocked. Leibniz died as a robber. Newton died as a king. However, the concept of a derivative had been developed almost 1200 years before Newton, and Leibniz by Bhaskara too. He provided differentiation of the trigonometric functions. For example, in modern notation, he established delta. He wrote delta sine x is equal to cosine x delta x. So this is nothing but the derivative of sine x. Bhaskara too also gave a statement of Michael Rolle's theorem, calculated that the derivative vanishes at a maximum, and introduced the concept of instantaneous motion of a planet in his collection Siddhanta Shiromani. Then in the 14th century, Madhava invented the ideas underlying the infinite series expansion of functions, power series, the trigonometric series of sine, cosine, tangent, and arctangent. These series have been credited to James Gregory, Book Taylor, and Newton. Rational approximations of infinite series, test of convergence of infinite series, the estimate of an error term, and early forms of differentiation and integration. All this was known in India. Madhava fully understood the nature of the infinite series. This step has been called the decisive factor onward from the finite process to ancient mathematics to treat their limit passage to infinity. Archimedes actually missed the concept of limit. So it is starting from the time of Archimedes, which is in fact the kernel of modern classical analysis. Parmeshwara Nambudri, a disciple of Madhva, stated an early version of the mean value theorem in his Lilavati Bhasha. This is considered to be one of the most important results in differential calculus and was later essential in proving the fundamental theorem of calculus. So roots of fundamental theorem of calculus were already there, which shows that the inverse character of the tangent and area problems. Torricelli was the first to understand the fundamental theorem of calculus geometrically, and this was extended by Gregory, while Varro established a more generalized version. And finally, Newton completed the mathematical theory. So as it happens in mathematics, somebody does or somebody starts, his name is nowhere. The person who is most popular, his name becomes, or everything becomes in his name. That's exactly happened with Pythagoras. Let us see Neelkanth. Following the footsteps of Madhva and his father Parmeshwara, provided a derivation and proof of arc-tangent trigonometric series and gave the relationship between the power series of pi and arc-tangent, namely pi over 4 as 1 minus 1 over 3 plus 1 over 5, etc., which is in literature has been credited to Gregory and Leibniz. Okay? So this series was known much earlier. Rather, a modified version of this series, which converges faster than this one, it was also known. I have written in one of my papers. I am not a historian. Whatever I am presenting, it is all what I have read in the books. Of course, I have gone through almost in last 49 years, more than 100 books. Now let us see what is about L'Hopital's. Of course, everybody knows L'Hopital's rule. L'Hopital's rule is not because of L'Hopital. L'Hopital's rule is actually due to Bernoulli. Anyway, this is what history is. L'Hopital is known as the author of the world's first textbook on differential calculus. But Jyestha Devan, 500 to 600, wrote the calculus text Yukti Bhasha in Malayalam, a regional language of the Indian state of Kerala, almost 150 years earlier. So who can say that calculus was not known in India? Now, let us see set theory. In mathematics, a set is defined as a collection of objects or elements, and set theory is considered to be a branch of mathematical logic. It has been documented that George Cantor introduced set theory to the mathematical world in 1874. However, during 875 AD, the Jain school of mathematics in India utilized the concept of sets. In their work, Jains introduced several different types of sets, such as cosmological, philosophical, karmic, finite, infinite, transfinite, and variable sets. They called the largest set as omniscient set, and the set containing no elements was called as null set. They also defined the concept of a union of sets and used the method of one-to-one correspondence for the comparison of transfinite sets. In order to determine the order of comparability of all sets, they considered 14 types of monotone sequences. Thus, Cantor alone is not the founder of the set theory. His major contribution was the mathematical systemization of set theory, now known as naive set theory, and the modern understanding of infinity. Next slide. Today, set theory is woven into the fabric of modern mathematics. Everything you see, set theory has entered. In fact, the language of set theory is used to precisely define nearly all mathematical objects. Next slide, please. Now I come to the word mathematics. The word mathematics was coined by Pythagoras. There is no doubt about it. It meant a subject of instruction, and its first part, math, comes from an old Indo-European root that is related to English word mind. The Pythagoreans grouped arithmetic, astronomy, geometry, and music together, and for several centuries, mathematics referred to only these subjects. After Pythagoras, several different definitions of mathematics have been proposed. Each one tries to define mathematics with a specific context in mind. For example, mathematics is like draft in being suitable for the young, not too difficult, amusing, and without peril of the state. This is the definition of Plato. Mathematics is the study of quantity. This is the definition of Aristotle. Next slide, please. I'm going to skip many definitions which have been proposed. I will just read few of these ones. Mathematics is the science of order and measure, Descartes. Mathematics is unshaken foundation of science and plentiful fountain of advantage of human affairs. Mathematics is concerned only with the enumeration and comparison of relations. The world best mathematician Gauss. Can we move, please? Next slide, please.
Next slide, please. Next slide.
So these are definitions of several other mathematicians and philosophers. Can we move to next one? Mathematics is branch of logic, that kind. Mathematics is the science of quantity. Peirce, mathematics is the science of self-evident things. Felix Klein, mathematics is the development of all types of formal, necessary, and deductive reasoning. Whitehead, and let me read one more. Mathematics is a game played according to a certain rule with meaningless marks on paper. This is David Hilbert. Next page, please. The whole of mathematics is nothing more than refinement of everyday thinking. This is Einstein. Mathematics is the art of problem solving by Polya. Can I have the next slide, please? Mathematics today is the instrument by which this. Okay, let us read this one. Mathematics today is the instrument by which the subtle and new phenomena of nature that we are discovering can be understood and coordinated into a unified whole. In this, some of the most advanced and newest branches of mathematics have to be employed and contact with an active school of mathematics is therefore great asset for theoretical physics. This is by Homi Bhabha, Fellow of Royal Society. He was a student of Dirac, if I am not wrong, and he was the founder of Tata Institute of Fundamental Research. I had the pleasure of visiting Tata Institute in 1973. Let us move to next slide, please. Mathematics has also been defined as several different other ways. I think I'm short of time, so I will move to next slide. A variety of quips and cliches can be defined mathematics. It is an art, it is a science. In fact, it is a queen and servant of science. It is what I use when I balance my checkbook, a game what we play with rules we are not quite sure of, and the apologetic favorite for students, something I was never good at, and the list can go on. Let us read the last one, Galileo. Nature is written in mathematical language. Let us move to next slide. Mathematics are like mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it is something entirely different. This is by Goethe. Goethe Institute, you must have heard. Let us move to next slide. We also encounter some negative views about mathematics, such as the idea that mathematics that is certain does not refer to reality, and mathematics that refers to reality is not certain. This is by Einstein. Then Sir William Hamilton, not the same Hamilton, algebraist, but he was the famous philosopher, logician, metaphysicist. He viewed mathematics in a way that may be constructed as a cruel attack on mathematics and hence on mathematicians. Let us see what he says. Mathematics frees and parts the mind. An excessive study of mathematics absolutely incapacitates the mind for those intellectual energies which philosophy and life require. Mathematics cannot conduce to logical habits at all. In mathematics, dullness is thus elevated into talent, and talent degraded into incapacity. Mathematics may distort, but can never rectify the mind. So cruel attacks have been made. Now I'm coming to a story from Buddhist Sutra, the falling peril of the blind man and the elephant. This is from Buddhist Sutra, is relevant to our attempt to define mathematics. Several prominent citizens were engaged in a hot argument about God and the different religions and could not come to an agreement. So they approached Lord Gautam Buddha. Once again, I have written 1887 to 1807 BC to find out what exactly God looked like. Buddha asked his disciple to get a large majestic elephant and 4 blind men. He then brought the 4 blind men to the elephant and told them to find out what the elephant would look like. The first blind man touched the elephant's leg and reported that it looks like a pillar. Next page. I'm sure that you must have heard this story, and I'm going to link it with mathematics. The second blind man touched its tummy and said that an elephant was an inverted ceiling. The third blind man touched the elephant's ear and said that it was a piece of cloth. The fourth blind man held on to the tail and described the elephant as a piece of rope. And all of them ran into a hot argument about the appearance of the elephant. The Buddha asked the citizens, each blind man has touched the elephant, but each of them gives a different description of the animal. Which answer is right? All of them right, was the reply. Why? because everyone can see part of the element. They are not able to see the whole animal. The same applies to God and to religions. No one will see him completely. By this story, God Buddha teaches that we should respect all legitimate religions and their beliefs. This famous blind man episode is not meant to disrespect any mathematician. We state it only to point out that any any definition of mathematics, however elaborate or epigamic, will fail to lay bare its fundamental structure and the reasons for its universality. This quote is from Herman Weil. Um, he was one of the most famous physicists. In fact, the definition of mathematics continues to change with time and innovation. Next slide, please. I will just read few lines and let us say, a proof is an explanatory note that the human senses can perceive and that leads the mind and intellect to establish the validity of a fact or argument. Proofs express subjective truth, not universal truth. Since humans have limited perceptive power, there are innumerable subtle assumptions that must be made during the process of proof, which are beyond human intellect. Therefore, any proof can never be exact. This is why we accept whatever truth can be established within our human limitations. Yet the great sages and rishis of history possessed in samadhi stage. That is very important. Extraordinarily subtle insight as well as unique experiences, which led them to establish certain truths. These are known as empirical theories and are simply well-founded empirical generalizations or laws about the properties and behaviors of objects that are obtained by examining a large number of instances and seeing that they conform without exception to a single general pattern. These theories could never be questioned and have withstood the test of time. One aspect such theories because of his total faith in the wisdom of these sages, or because he believes this to be primary or the sole path to knowledge. Next page, please. It should be noted that the proof has different shades of meaning depending upon the field in which it is considered. For example, within the logical system, the burden of a proof in a civil court is preponderance of evidence, whereas in a criminal court it is beyond a reasonable doubt. In scientific world, physics, chemistry, engineering, truth is established by experiments. In the business world, statistical analysis of data are performed and conclusions are derived. In political and international matters, organizations or group of individuals are entrusted with finding the truth of a given issue, and they come up with their conclusion based on classified intelligence reports, site visits, interviews, and other such activities. In a religious sense, proof is difficult to even describe. In scientific measurements, due to uncertainty, the absolute truth cannot be found, although we may get extremely close to doing so. Next slide, please. Can we go to next slide? I'm sorry, let us go to previous slide. A proof of a mathematical state is a logical argument that shows the statement is true according to certain accepted standards. It is believed that the idea of proving a statement began about 5th century BC in Greece. Initially, philosophers developed a convincing each other of the truth of particular mathematical statements. They used definitions and axioms to do this convincing. Over time, these ideas were collected and organized in 13 books by Euclid called Elements of Mathematics. Recent research on Indian mathematics shows that there were other methods of investigating mathematical ideas other than commonly accepted proof methods and described by Euclid. Now, next slide, please. I'm just going to read and then skip most of it. In fact, Indian mathematicians wrote commentaries on the works of earlier writers to elaborate ideas, to find other ways of achieving results and of making new and useful applications. The word upapatis in Pali, Sanskrit, and Marathi languages is used for proof. I don't know when this word started, but I am sure that it is thousands of years old. Following are some of the important features of upapatis in Indian mathematics. The Indian mathematicians are clear that results in mathematics, even those enunciated in authoritative text, cannot be accepted as valid unless they are supported by yukti or upapati. It is not enough that one has merely observed the validity of a result in a large number of instances. That means if you keep on trying for any number of cases, that proof is not complete. Let us move to the next one. So here I have pointed 9 cases. Let me read just the number 9. While Indian mathematicians made great strides in the invention and manipulation of symbols, in representing mathematical results and facilitating mathematical process, there was no attempt as formalization of mathematics. There is one more somewhere I have written. Anyway, it should be noted that in all existing literature, no mention has been made about the contribution made by Indian mathematicians, or the fact that these mathematicians viewed the concept of proof differently than what was described by Euclid. Today, when I teach, and the moment I write theorem and start writing proof, students hate me. I can see the future. Within few years, different books will be written for different students. Particularly for engineers, it will become no theorem. It will be just the formula, and it will be just sitting in front of the computer, put the data, and verify the result. This is what is the future of mathematics. Of course, some crazy guys will continue. Let me read the last paragraph. There is a widespread notion that once something has been proved mathematically, then it is as it were some in stone that we have mathematical proof that remains true for all time. Not so, says James Meyer. He is coming up very fast. According to him, a proof is always dependent on whatever system of assumptions and rules of inference used to create the proof. He writes that most mathematical proofs that anyone will encounter fall a long way short of idealistic concepts. Next page, please. So let me read. While the definitions of mathematics and proof continue to change with time and innovation, mathematics rewards its creator with a strong sense of aesthetic satisfaction. It helps us understand man's place in the universe and enables us to find order in chaos. Under certain axioms, mathematics is the most absolute, everlasting, precise, significant, and universal subject. It is perceived as the highest form of thought in the world of learning. No doubt, mathematics is one of the greatest creations of mankind. If it is not indeed the greatest, mathematics will live forever. Last slide, please. These are the two references. What I have done from the first reference, I have taken just 3 pages. And if you have any doubt about the dates which I have given, Professor Lakshmikantam, he spent almost 50 years to calculate the correct dates. So some of the dates you may not agree, but these are correct, and I am very sure that sooner or later these will be the real dates, if at all some person will write the correct history of mathematics. Thank you very much for listening, and I really enjoyed giving this lecture. Once again, I am not a historian. I am a classical mathematician, but my interest now is more towards history. Thank you very much.
Thank you, sir, for such an excellent speech, but it seems like some of the participants want to ask some questions. As the time is too short, so I would request Professor Surya Kumar Biswas, faculty of our department, to ask some selected questions to Professor Ravi P. Agarwal. Sujoy, carry on.
Yes.
Yeah, go ahead.
Good evening, sir.
Good evening.
Good evening, sir. Some questions have come from our participants.
Sure.
Now I am telling you one by one. First, that any question from Sri Devi, any concept that is taught by introducing the history or the origin of the concept may interest the learners.
Okay, there is a famous phrase, and the famous phrase is, no subject loses as much as mathematics without history. Okay, you see my book, Creators of Mathematical and Computational Sciences. You will find that without history, mathematics is not complete. Okay? So history of mathematics plays a very, very important role. And you will see that once you read the history and you read what is their contribution, you will get some new ideas. Next question, please.
Okay, sir. Thank you. Next question from Pratap De. How do you differentiate between ancient mathematics and modern mathematics?
Okay. Ancient mathematics was mostly constructive. Okay. They didn't bother much about the proofs. The recent mathematics is based on logic, and it is actually main thing is proof. Actually, mathematics and proof go together. Without proof, there is no mathematics. Okay. However, in earlier periods, we started our rishis and saints. They started with going to samadhi state, observing the things and writing down. Whereas now we are following whatever is done by Euclid or whatever Greece has imposed on us. So, as I mentioned in my lecture, things are changing, and within may not be in my lifetime, in your lifetime, the definition of mathematics will be very different, or you will have a very different type of mathematics. Next question, please.
Okay, sir. From Vishu Raghav, how the sum of all natural numbers come out to be minus 1 by 12? Is there any proof regarding these?
Yes, actually, if I remember correctly, Newton's supervisor, he proved 1 plus 2 plus 3, etc., or 1 plus 2 plus 4 plus 8, etc., is equal to minus infinity. What he did, 1 over 1 minus x is 1 plus x square plus x cube, and so on. You write the value of x as 1, left hand side, write the value of x as 2, you will find minus 1 over 2, and in the right hand side you will get 1 plus 2 square plus 2 cube. Now, it is the concept of negative numbers was not known 400 years back. It was not known in Europe. Whereas in India, the concept of numbers, negative numbers, was known almost 1800 years back. So it is wrongly applying what is known as the Taylor series. 1 over 1 minus x is convergent only when modulus of x is less than 1. So you see, even Newton's method or Newton's expansion of binomial theorem for every number is based only on the observation. What he did, he interpolated the Pascal triangle. He saw the pattern. He saw what happens when the number is half. He interpolated between number 1 and number 2. That means between the two rows of Pascal triangle, he was able to find the values. He didn't prove that. The proof of that one came much later. Okay? So this is how the mathematics works. You see the pattern, based on the pattern, you just make a claim or conjecture that this is what is true. Okay? And later mathematicians, or in your lifetime, you yourself keep on proving. So this is how the mathematics goes. We all make mistakes. Mathematics is, I will say that there are so many different type of fallacies in mathematics, and I can never say that any mathematician has never made a mistake and published. We all have made mistakes, and then after publishing, we have realized that there is a mistake. Okay, so y minus 1 over 12, you can have any negative number and you can show that right hand side is positive and left hand side is negative. For example, the concept of imaginary numbers. Although Euler is supposed to be the creator, or he understood, but much later, at earlier stages, he didn't understand the concept of imaginary numbers. So it is all game. Mathematics is full of tricks. Mathematics is full of assumptions. Mathematics is full of anticipation. So that's how the mathematics continues. Okay, if you have any other question.
Yes, sir.
Okay,
Sir,
go
next
ahead.
question from Nozul Haq. Question is there any ancient version of modern mathematical branches such as game theory, network model, epidemic modeling, etc. in our ancient Indian?
What is MCM?
Ancient India.
Oh, ancient India. I don't think so, because most of the theories which are known to us in ancient India were constructive, and all these game theory, etc., have started after set theory. So whatever courses you are reading now, so-called analysis, so-called topology, so-called linear algebra or algebra, abstract algebra, or game theory, all these subjects are after set theory. So when India introduced set theory, it was for the different purpose. Okay, so no, all these subjects which you mentioned, these are new creations in mathematics. Okay, next question.
Yeah. Suja,
Okay, sir.
we have to stop now because the time is up. So I have one question, Professor
Sure,
Agarwal.
sure.
So last year I went to San Antonio
Okay,
to attend. So I met some friends over there. They are my
okay,
long friends.
yes,
Being an Indian, I am very proud of that. All the mathematical events are introduced in India, but there is still doubt of it. Iranian, my friend Iranian,
yes,
right now he is in Pennsylvania State University. He claimed that all the mathematics are done in Iranian, and the Chinese, my friend Chinese, they claim that all the mathematics have been done. Hello. All the
yes, yes,
mathematics is done in China.
yes,
So at some time, if you go to the book of Smith in the
yes,
history of mathematics, they
yes,
fully deny that all are done by Europe. You mentioned before, because they
yes,
mention it. Just look at the Babylonian and
yes,
culture.
yes,
Pyramid and all these things, they are constructed on the base of mathematics. And
yes,
Mesopotamia and Greek is very near to Babylonian. So the
yes,
culture to Greek, that is why culture developed, but India is far ahead. So consider the European mathematics consider the culture flows from Greeks to UK, then Iran, and then India. But that is a matter of confusion. So I
yes,
know a person, perhaps know, R.C. Gupta
yes,
in Russia.
yes, 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 I know him.
He's produced a lot of things on history of mathematics.
Yes,
And also claim sine 1 plus AB, sine formula, and sine AB,
yes,
all are originated from the Sanskrit.
yes.
What is your idea?
Okay.
That is a controversy, right?
I'm going to give you a very blunt answer. Okay. And the blunt answer is, it is we are responsible for it. How we are responsible? Let me tell you, in 1978, first time I went to Germany, I saw one German professor doing something, and other professors who are listening, they are praising so much that if this is not done, the whole world will collapse. And we Indians are criticizing ourselves. I'm doing something, immediately after my lecture, somebody will write to me that what is the proof? Okay.
Yeah.
Now the proof is, what is the proof God is existing? What is the proof of, I mean, there are many instances I can give. You cannot give the proof. Okay. Now one has to accept from the, I mean, if somebody has written, that is not the proof. You should see the facts. Okay. I have given you, for example, for equinoxes, the number 27,000 something. Okay. Why not you go to internet and see? You will find that it is written on internet that it is known from the Vedic period. Okay. Now, when Vedic period started thousands of years back. Vedas were written thousands of years back, right? But you will not find this on the internet. You will find that Vedic period started 1500 BC. So we should write more on internet, because internet has become the media. Whatever is written on internet, people have started accepting. Many things are wrongly written. You can write anything you like on internet.
Yeah, right.
So my conclusion is, or my answer to your question is, that for this, we are responsible. Okay? We criticize each other, and you do something, I criticize, I do something, you criticize. That is what is going on. Now, I refer to two books by Stephen Knopp about the Vedic culture. You will find thousands of examples all over the world that Vedic culture was all around. Okay, let me just give an example, and I think Professor Muldowney will be happy to know. Right from the beginning, the first creation by God, according to our philosophy, was Manu.
Yeah.
M-A-N-U. The word man has come from Manu. Okay?
Right.
So
Manu.
nobody realizes this unless you read it. So
It should be.
I will suggest that read the book of Stephen Knopp, and then your mind will change. The book I have written, Creators of Mathematics and Computational Sciences, read that.
Okay.
You will find the answers of your questions. Okay?
And there is another question.
Now,
1684,
what is most important to me, that this book has reached in thousands of hands.
Yeah.
And not a single person has written to me that it is wrongly written. So I'm happy. Now I have written 2 papers on
I am
Pythagoras.
proud of that one. I am proud of that one. You have given effort to write a books like this way. So I am proud of that. But another question is that you have mentioned 1684, calculus was invented by Leibniz and Newton. But there is a debate.
Yes.
If you have see the book, War of Calculus, that is the book. They claim that it was invented. What is your opinion in this regard?
Okay, there is a lot of controversy. There is so much of controversy about Leibniz and Newton.
War of Calculus.
Yes. Now let me tell you a little bit. There is no doubt that Newton used the concept of calculus first, but he was afraid of publishing. He kept the ideas with him. Okay. Now, as far as about Leibniz is concerned, the history says that he came across the ideas of Newton. Okay. And he developed the calculus. But there is a basic difference between Newton calculus and Leibniz calculus. Leibniz calculus was from mathematical point of view. Newton's calculus was from physics point of view. Okay, but essential idea is same. Now, after that, there was a lot of feud between Newton and Leibniz. Okay, what is most unfortunate thing, and for which mathematical community or the whole world will never excuse Newton, is that Newton was the president of Royal Society, and all the letters written, all final statements written were by Newton. Okay. Now, when Leibniz died, his statement was that I could break his heart. Okay. As I said during my lecture, Leibniz died as a robber. The only person with him was his secretary. Nobody else was there. Whereas when Newton died, he died like a king. So why there is so much of partiality? We all are same. Okay? The books written by Europeans on history of mathematics, that history is continuing. Okay? We are not prepared to change it. We have accepted it. And our children are studying the same thing. That is what is unfortunate. Nobody wants to tell that Pythagoras theorem is not due to Pythagoras. Neither he gave this theorem nor he proved this theorem. Okay?
Yeah.
The proof of Pythagoras.
Thanks, Professor Agarwal.
Pardon
Thanks
me?
for your kind lecture. Most important information like both the Vedic mathematics originated from India. So nice lecture. So have you published your book?
Of course, it was published in 13, I think.
Oh, thanks. Okay,
The last page, first reference, it was published in 13.
Okay, thanks. So our thanks again for your nice lecture. More info. Indian, we are lectures. Next speaker, Muldowney. Pavanjan,
Yeah.
will you please say something?
Yes.
Pavanjan.
Now, yes.
Okay.
Now start the second lecture. For starting the last lecture, I would like to tell some about introducing Professor P. Muldowney. Professor P. Muldowney studied at National University of Ireland and then at the University of Michigan. Currently, he is a Vice President of Calcutta Mathematical Society. He had been collaborated in the theory of integration with Ralph Henstock, founder of the theory of gauge integrals, generalized Riemannian integration. His area of the work is infinite dimensional integration, involving the theory of Brownian motion, Feynman path integral in quantum mechanics, and stochastic integration in probability theory. He had published many books. Now, I would like to request Sir Professor D.K. Ganguly. In this session, is also chairperson and proceed this session of this program. Sir, Professor Ganguly sir,
Hi,
sir,
are you okay? Muldowney?
Yes, I'm here. Can you hear me?
Let me introduce more because Muldowney is my friend. I want to miss one thing. You know that Ralph Henstock is the pioneer of the gauge integral or Stock integral, and Muldowney is the last student of he did work process of Henstock integral in the he has written number of books, and so I request Muldowney to start your talk. Muldowney.
Okay, I hope everybody can hear me, and I hope you can excuse me for not being experienced with this online system. Certainly, I will not be able to compete with the lecture of Professor Agarwal, which there was so many things in it, and surprisingly, so many things which are relevant to some of the things that I want to talk about. I should say first, it is really is a great pleasure to be able to address this webinar, and I do appreciate the invitation, and I particularly appreciate the presence of Professor D.K. Ganguly, who I know for many years, and I can also I think appreciate what Professor Agarwal said, that when he first visited Calcutta, that it changed his life. That he married and had lived happily for 50 years after that. So, in a sense, I too have had great experiences in Calcutta, particularly adventures and expeditions, and with Professor Ganguly and other people in Calcutta, both in India and in Ireland. It truly is a pleasure. I will continue, and in fact, well, perhaps I would now try to operate the system. Let me see if I can get this. Okay. 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 This is good. The subject is Feynman diagrams. Feynman diagrams are a graphical device in physics, which are used to analyze the interactions that take place in quantum mechanics. Now, I'm aware that Ramakrishna Mission College is strong in physics. The contribution really in this subject is in relation to certain mathematical issues that arise in this area of physics. In fact, before, well, let's take a look at I'll not be as skillful now as the previous speaker in operating this system, but this is a Feynman diagram. Let me see. I need to. So. This is the first ever published Feynman diagram. It appears in an early paper by Feynman around Richard Feynman around 1950 or thereabouts. And there is a kind of, there are many versions and forms of Feynman diagrams.
Professor Muldowney, you are actually this sharing is stopped. You please start the sharing. You start your sharing, sir.
I just
stop, sir. Stop. Yes. You see? Yes. Now it is visible. Yeah.
It's okay, is it? Oh,
yeah.
Okay. Well, perhaps then I should stick to I should stay with the slides and not. Okay, let me try one more thing. I wanted to say something about Richard Feynman himself. What I'm showing here is a video of the Challenger space shuttle of 1986. If I play that. I will stop it there. And the reason I'm bringing this up is because Richard Feynman, he wasn't a celebrity physicist like, say, Einstein was, but he was certainly, I think, the most prominent physicist of the middle part of the 20th century. He became famous in connection with this Challenger disaster. The reason he became famous is because he was brought in the investigation into why it happened. Now you can think that this huge corporation, this NASA, that there was such a disaster had happened, that there was a lot of cover up. Now the Feynman was brought in the investigation, and he became famous in a television program which showed him getting right to the point with a precise explanation of why the Challenger spacecraft blew up. So I'll just play a little bit of that. It's quite short. Okay, this is very typical of Feynman. While the NASA and the corporations which were involved in this would have gone to greater lengths to cover up the problem, there would be huge volumes of reports, and the real truth of why this disaster happened could easily have been covered up. But Feynman, in public, on television, got right to the heart of the problem and showed what actually happened. It was the failure of this. We call it a gasket. It's a rubber seal which would keep the fuel from leaking out. The seal did not work. The fuel escaped. The spaceship blew up. Okay, now in a sense, that is a little bit relevant to the talk, in the sense because Feynman had this particular gift for giving clear explanations of quite difficult things. They're not easy explanations necessarily. And again, I'm not here to talk about physics and the explanations of physics, but at the same time, there is the point raised by Professor Agarwal when he talked about Ramanujan as being the greatest intuitionalist of all time, which I think must be true. You know, when you read what Ramanujan presented, that he had this sense of what was the essence of things were. Now, Feynman is also said to be the greatest intuitionalist of his time. That's in a different subject, in physics. But Feynman had this uncanny ability to discern how things worked in physics. The point of contact between Ramanujan and Feynman. Ramanujan was, as I understand it, essentially a self-taught mathematician. When it came to the advanced mathematics, he learned it himself. Feynman actually did the same thing. He was a self-taught in mathematics. He ran ahead of his class, the books, absorbed it with his own particular insight and gift for the subject. One other point of contact with Professor Agarwal, he mentioned John Wheeler as one of the many people who have acknowledged the influence and history of the Vedas and Indian literature in particularly in the history of mathematics. Now, Wheeler was Feynman's supervisor. John Wheeler was a physicist like Feynman. He was Feynman's supervisor, PhD supervisor, and collaborator for some time. In fact, there's many other points of contact with Professor Agarwal's very interesting lecture. But I should move on and try to talk a little bit about the Feynman diagrams, where they come from, what are the mathematical issues that which arise in it, and so on. Now, again, if we look at this particular diagram here, a basic Feynman diagram, what it appears to, I'm not going to attempt to explain everything here, but this is a displacement time graph. You have time in the horizontal axis, and you have distance on the other. So you think, if you look at my hands, you think that what we have here is two charged particles approach each other. Now, we make a distinction here between classical mechanics and quantum mechanics. Classical mechanics arose around the same time as the Leibniz and Newton theory of calculus, say what, 300-400 years ago. But classical mechanics, they developed it. Newton in particular developed it in order to explain physical theory. So in this case, you have, let's say, two charged particles approaching each other. According to classical mechanics, they exert a force on each other proportional to the square of the distance between them. You see, so as they come together, they sort of detect each other. They begin to slow down. Then the force between them gets larger, and they repel each other. Okay. Now, in the Feynman diagram shows a different process taking place. There is an interaction, but it's not so much like that. It's not this classical mechanical picture. But what it is that the two approach each other. It's as if they don't know each other are there. They're coming together. Then suddenly something happens, bang, and they move apart. Now this is the interaction, the particle exchange, a little explosion that takes place. In this case, it's an exchange of an exchange of a photon, and this is quite different. You see, so if I go back and look at the diagram. Okay, there are many kinds of interactions. Now, where are these things coming from? Scroll down. Oh, okay. Before I go, the Feynman diagrams, they come from Feynman integrals, and there are certain mathematical problems in the Feynman path integrals, which these pictures are derived from. And I became interested in some aspects of those things, and that is what I work on. So where do these phenomena come from? Where do the physical phenomena come from? Well, this, I think, probably most people here will have seen pictures of cloud chamber interactions. These are small subatomic particles which are crashing into each other, producing new ones, and so forth. It doesn't have to be exotic like that. Personally, I have not been in a physics laboratory since about not quite 50 years. Yeah, 50 years ago. But in fact, these phenomena take place, or they're all around us all the time. If we go to get an X-ray in the hospital, then these processes are taking place. Alpha particles are projected into our bodies, and we get a picture. We have an old television's technology, like cathode ray tubes, is the one I'm familiar with at my age. I don't know about flat screen TVs, how they work, but cathode ray tubes was electrons projected at a screen, and you produce a picture. So we have semiconductors, we have solar flares. These phenomena are all around us. They require a physics explanation, and this explanation is provided by quantum mechanics. So if I scroll down, the sources for the theory of Feynman diagrams and of the path integrals, of which they are a kind of simplified version. This book is the first one, Quantum Mechanics and Path Integrals by Feynman and Hibbs, 1965. This is a similar book by Lawrence Schulman. It covers much the same ground, but it gives a different take on it. It gives a different kind of take on it, and it's useful. I found both of them useful. My contribution is in chapter 7, I think, of this book here. Again, it looks at particular mathematical issues which arise in the theory of path integrals. And before I move on from sources, let me just pause this at the moment and go down to this. Okay. This is a rather famous quote from Feynman's Lectures on Physics in Volume 2, Chapter 19. And it kind of gives the basic idea which is used in Feynman's version of quantum mechanics. Okay, Feynman says, when I was in high school, my physics teacher, whose name was Mr. Bader, called me down one day after physics class and said, "You look bored. I want to tell you something interesting." I can't imitate Feynman's New York accent, which is it should be imitated because it's quite interesting. Anyway, so Mr. Bader told me something which I found absolutely fascinating and have since then always found fascinating. Every time a subject comes up, I work on it. In fact, when I began to prepare this lecture, I found myself making more analysis on the thing. Instead of worrying about the lecture, I got involved in a new problem. The subject is this: the principle of least action. The principle of least action. Now, we have talked a little bit about classical mechanics. That's, I suppose, the basic equation of classical mechanics is force equals mass times acceleration. Now, just as calculus didn't begin and end with the Vedas, it didn't begin and end with Newton and Leibniz. It continued on into the 19th century, into the 20th century. Classical mechanics continued on into new versions, new formulations into the 18th and 19th centuries. Euler, Lagrange. Euler and Lagrange developed this idea of action. If I could the idea of action is that a system seeks to minimize, in a sense, the total expenditure of effort, if you like, in going from an initial configuration to a final configuration. So if I were to throw a projectile, okay, I throw it. Okay, happens here is that the path followed by the projectile is such that the total amount of action for the whole path is minimized. Now I've used the word effort. The word action is technical meaning, and I'm hoping that we will touch on it as we go through this talk. It's a curious idea and a little bit slightly mystical in a sense. How can an inanimate object, if as it's thrown, know what the future holds for it? Now there are many good explanations of this, but for a very good and serious exposition of this subsequent, that's post 17th century, post Newton version of mechanics. I find this an excellent book. As Cornelius Landshaw's The Variational Principles of Mechanics, and in many ways it explains the idea of action in mechanics. Now, action is, in a sense, like the connecting idea between classical mechanics and quantum mechanics, especially in the hands of Feynman. Okay, so if I move on here in my own way with this, I said that these Feynman diagrams come from the integrals devised by Feynman. Now, if we just take a look at this, with certain. Can I bring this up a bit? Yeah, okay. There's an integral symbol in this. There's an integration in it of some sort. That's good. Some kind of variable of integration. That's usual. You know, you have the integral of y squared dy. It's y cubed over 3, something like that. Okay, so in fact, we have a function to be integrated. Okay, this is an exponential function. It's got e in it. That's not unusual. Now, the e to the power of I've got I over h. I is the square root of -1. H is the modified Planck's constant. It's just a number. S is the action functional. Is used in this integral. The result of the integral is this expression psi. Now, psi is the fundamental quantity on which quantum mechanics works. It's called the wave function of a particular system. So if we were to talk about two electrons coming to collide with each other, to understand it, you would want to know to understand it in quantum mechanics, you will want to know the wave function. If you want to understand it in classical mechanics, you will want to know the charge of one of the particles, the charge of the other particle. You will want to know the distance between them, and you will calculate the first charge multiplied by the second charge and divided by the square of the distance between them. Now that is the classical mechanics formulation or theory for the interaction of these two charged particles. It does not really work in detail. And these problems were discovered, as I'm sure most people here know. I know that this college is strong in physics. So you'll bear with me for maybe over-explaining this. but to explain what actually happens, which is not really like this, but more like going through, an explosion happens and it goes back. Now, you need this wave function to do that. Now, the contribution of Feynman was to work out the wave function for quantum mechanical systems by means of integrals of this type. Okay, so these path integrals. So if I move on, I'm aware that in actual fact we've probably already exceeded our time for these lectures, but I can in a sense what I need to do here is my interest in this thing was in this integration here. It's quite complicated and difficult. It's not simply an ordinary integral. The variable of integration here is x dot. What do I mean by x dot? It's not like integral y squared dy. It's something else. So I can maybe go back and look at this slide a little more detail. We are talking here about a process taking place over periods of time, which for values of t between an initial time tau dash. Think of tau dash as simply time zero, so call it zero, and a final time tau. An initial position, let's say, if we're talking about a single particle, its initial position, displacement in space, is zero. It starts from starting point, some origin of motion. And its position is, we denote by xi. In between times, there are all the possible positions that this object can take. It can move about from a displacement of zero, let's say from here, moving them up to here. Okay. So in between time, there are many positions possible. If it is a free particle, with no external influences at all, according to classical mechanics, it should go, the first law of motion of Newton, every particle will continue in its state of rest or of constant speed throughout its motion. Okay, so in this case, the particle will go in a straight line from the initial position to the final position. However, if there are forces acting on it, then the particle can take a path of a projectile, for instance, or various other paths. So in that case, we have in between the initial position and the final position, we have all the intermediate positions. You see, xt at time t. So we have to consider all possible trajectories of the particle, or in general of the quantum mechanical system, and that's denoted by this here. This is xt for all values of t and all positions. Now, from this trajectory, which can be summarized as simply x dot, you calculate the action for the system, and that is the kinetic energy minus potential energy at each location in space, and you integrate that along the path or trajectory taken by the particle. That gives you the action. The classical physics, classical mechanics, the particle somehow knows that to follow the trajectory which minimizes the total action for the system. Okay. Now, what Feynman did was to look at all, not just look at the classical path, which is the path of least action, but to look at all possible paths to sum this quantity, consider this functional of the paths, each the power is exponential functional, and to average them all over all possible paths. The result, if the result, if there is an average value or an integral, is this. Okay, so can I ask Professor Ganguly, am I being heard? I'm not sure if Professor Ganguly. Yeah, can I be heard? Okay.
Huh?
Okay, so you can hear me. So, okay, in that case, I will continue.
Yeah, 15 minutes. You can continue. You can continue.
Okay, thanks. I just wasn't sure. I'm not familiar with this system, you see, so or this online thing. So I hope you'll forgive me for this. Okay, so I continue here. Okay. Okay. Then, now, if we look at the integrand for the path integral, okay, it's this expression here. That's a kinetic energy minus potential energy. Now, kinetic energy is, for a single particle, is half of the mass times the velocity squared. The potential energy at any given point is the total work done to bring the particle to that particular point in space. Okay, that particular. You subtract those two things, and then to get the total action, you integrate that expression along the path with respect to time. Now, I just have to do some technical calculations here. See, okay. So if we look at this time integral for the action, we can integrate these two functions separately, and then because this is an exponential, the exponential of a difference or the exponential of a sum is the product of the two exponentials. Okay. Now, what we do, or what Feynman did in his investigation of this, was to expand the second exponential as an infinite series. So e to the power of some quantity is what's it? It's 1 plus the quantity squared divided by 2 factorial plus the quantity cubed multiplied by 3 factorial divided by 3 factorial, etc. to infinity. Now the quantity in this case is simply oh, I think there's a mistake in, isn't there? I'm sorry. Yeah, there is. I have a square root of -1 there, and that should also be here. So, but let's not worry too much about these details. The general idea is that you expand the second exponential as an infinite series, and then remember the wave function was the integral of this of all possible trajectories, with the variable integration being the trajectory, like dy in one dimension. Okay, now there isn't too much more of this very technical stuff. So this is if we compare this, what has happened here? What has happened is we have turned the integral of an infinite series into an infinite series of integrals. Okay, we've exchanged order of integration, the integration operation, and the summation operation. Now, in any integral, you can do that if you're only adding two things. If you have the integral of f plus g dx or y, whatever, it's the same as the integral of f dx plus the integral of g dx. So the integral of a sum is the sum of the integrals. That's provided it's a finite sum. But if it's an infinite sum, yes, you can do it sometimes, but not always. Okay? I said we'll come back to this point. In fact, I think maybe we should pause for a moment and say that we've now encountered two mathematical issues. The first one is, what is the meaning of this integral over a domain of trajectories? What does all this mean? It's certainly not like integral y squared dy, you know. That's we know that sort of thing. We learn it at a young age. It's something. So there are big mathematical issues here, and they were recognized from the very beginning. It was the first thing, in a sense, that occurred to Feynman as he wrote this stuff up in his PhD thesis with John Wheeler, who was mentioned by Professor Agarwal. He wrote it up in his PhD thesis in 1942. He returned to the subject in 1947, 48, 49, and published essentially his thesis in a physics journal in 1949. And he mentions this particular problem. What does this? Can this possibly mean? We can't deal with it like he's dealt with by Newton or Leibniz. We can't deal with it like the ancient Indian experts like Bhaskara and Madhava, mentioned by Professor Agarwal. The problem has been around for a long time. How do you do this kind of thing? It's been around from ancient times, 5,000 years ago, right up to the present, really. Okay, so that's the first problem. What does it mean? Now, Feynman did give an explanation of it, and we hopefully we will, if we don't exhaust our time, which we have, I'm afraid, but I'll continue until I'm told to stop. So, Feynman did give an explanation of this, but he wasn't quite satisfied with it. And I remember, as a young guy with no particular authority I actually wrote him a letter, and surprisingly, he's like that. He was a person who was not very official. He had a particular kind of personality, so he would acknowledge unimportant people, nobodies like me, but he wouldn't deal with the great. He wasn't scared by NASA, for instance. You know, he wasn't intimidated by them. He came in and took his little coffee cup full of ice water, and he took a little rubber gasket. He did his experiment on them, and he blew away all the bureaucratic stuff that was being put forward in order to preserve careers and fortunes and grants and corporations and all the rest of it. And he just exposed it right there and then in 2 minutes on live television. So what I'm saying is that Feynman wasn't a very official type of person. He was very much to the point. So he actually replied to me my letter and explained why he did what he did. He wasn't too concerned about the finer points of mathematics, and rightly so, because it really wasn't a thing he should have wasted time on. He had much bigger ideas to deal with. So if there are two mathematical problems here, and if I have time, I hope to say something about them as to how they can be approached from the viewpoint, from the with mathematical tools that we now have, which were not available to Feynman at the time. So what I haven't done yet is to connect the this Feynman integral and its expansion in an infinite series of integrals. How is that connected to these amazing Feynman diagrams, which are apparently highly intuitive and extremely useful to physicists? Okay. So this essentially is the basic explanation for the thing provided in Feynman's early papers about 1950 or so, and then written up very well and very clearly in this particular book, which was out in 1965. It was co-authored with Albert Hibbs, I think was a student. A student of Feynman, I mean. So the idea of this is that for each exponent p, well, p takes a value of 0, and then 1, then 2, then 3, then 4, and so on like that. For p equal to 0, well, of course, 1 divided by 0 factorial 1, this is 1. P equals 0, that's 1. So we get a contribution of 1 from this. So we're left only with this expression here to integrate. The first term of the series, this part's all 0. Now this is simply corresponds to essentially Newton's first law of motion, that a body continues in a straight line in a state of uniform motion if there is no external force acting on it. So by taking p equals 0 here, we're eliminating the contribution to the interaction to the system of the external force. So the electron, let's call it the electron, will start from a starting position and will travel in a straight line to its terminal position. Okay. Now for p equal to 1, and I've left out quite a bit of the technical stuff here. There's another, let's say, page or so of explanation. It's all in this, and I have gone through it also in my own. I've given essentially the same thing, Feynman's explanation of it in chapter 7 of this book. So in that case, what happens is it's like the effect that happens is two charged particles approach each other. They move as if neither one was there initially. So it'll go in a straight line. Then suddenly it will see something, an explosion will take place. That's this here. This, and I think in Feynman diagram terms, is the emission of a photon small particle of light. Okay, light is a wave, so it's written as a little wavy line here. Okay, now when after that happens, the particle then forgets about the external force. There's no further external force, and it continues on in a straight line for the rest of the history of the system. Okay, so that's p equal to 1. Now for p equals 2, at 2 times, this is, let's say, t1, this is t2. Two emissions take place, 2 little explosions take place. Other than that, the particle acts as if it is a free particle with no external force. So this is not at all like classical mechanics. It's quite different. And so on. For p equals 3, we have this, something like this. For p, and this, of course, is an infinite series. Okay, so there are infinitely many little diagrams of this. sort. I am simplifying this a little bit, but that's the general idea of it. These are the Feynman diagrams. They come from the Feynman integral after you expand one of the factors as an infinite series, and after you exchange the order of integration and summation. Okay. Okay, one or two more points about the physics of this. As far as I understand it, just from general reading of the thing, it's not my field, so I don't claim to know anything in detail about the physics. The physicists then know to select which of these interactions are important. Generally speaking, as far as I understand it, only the first few terms of this infinite series are going to be physically significant. Now, again, I can be challenged on all of this. I don't claim to do it, but anyway, that's the thing. Now, summarizing here, again, the mathematical issues. What is the meaning of this? First bit, the meaning of this path integral of Feynman, and secondly, what is there a justification for doing this? See, from a mathematical point of view, if we see something like this, even if we don't understand the physics very much, we can immediately see, I think, that there is some problem with this. Everyone can see this. And in actual fact, there's an awful lot, there's a huge literature, mathematical and physics literature about this calculation here, the path integral. What actually does it mean? Feynman gives a meaning for it. Why are we not satisfied with that? Feynman was reasonably satisfied with it. But to be honest, I think it's one of the best explanations of it. The one that he gives, it's a good one, but isn't it actually not complete by any means? The second problem here is one that I have rarely seen, and never really seen addressed in the physics or mathematics literature. But yes, for people who are interested in the theory of integration, it's definitely a problem. You know, you simply cannot generally do this. You can't. You can very often can, but they're only under certain conditions. Can you exchange the order of integration and summation to infinity? So, in a sense, my talk is about this. I think I should not push my time here too much. I know we're well over the time, but what I should do is at least give it take a look at how this these two problems can be addressed by means of integration theory. I've put up here some problems that arise in integration. This first integral is correct. The expression I'm integrating here is in fact very closely related to the quantities which you have to integrate. The quantities which you're integrating in Feynman's thing. This is a harmonic functional, I suppose, like sines and cosines, which we have here. So these are quite like that. The first one is correct. The second one is false. It's because of the second one. These two integrals are found in tables of integrals. They're around for a long time. First one is correct. The second one is known to be incorrect. In fact, Feynman had quite a few of stuff like this in his book and in his paper. You know, where the stuff is done rather loosely, and it can be corrected, but it has to be done very carefully. The second thing is got from the first one, differentiating under the integral sign. I won't go through the details. I haven't got time, but it doesn't work. So it's exchanging the order of two limits in an integral. You have to be very careful doing it, and that includes exchanging the order of integration and summation to infinity. Okay. Okay, so we've had. I'm a little bit embarrassed here because I'd written these slides before. I had to leave out an awful lot of stuff here. I left out the contribution by Cavalieri, for instance, who came before Newton and Leibniz. Cavalieri is mentioned in Feynman's paper and in the book. He says when he was doing his integral, he said he felt as Cavalieri must have felt when he was calculating the volume of a pyramid before the invention of calculus. So, the methods, as I understand Professor Agarwal's lecture, Madhava and from the Vedas, the Vedic literature, Bhaskara and so on, they have been doing this about 3,000 to 4,000 years in advance of the squaring of the circle and all that kind of stuff that is done in this. That is integration, properly speaking. When you come down to Newton and Leibniz, you get this new, quite remarkable thing where you got this differentiation, you see, taking derivative. And we get the idea that integrating is the reverse, the inverse of differentiation. That's a very good idea, and it's I think it's such an overwhelming idea that it imprints itself on the minds of our minds at the age of 16 and 17 and 18 when we hear it first. I think that's what integration is. Of course, it's like plus and minus, multiplication, division. You got differentiation and integration. I find that a quite restrictive idea. And I get whenever I say that it's restrictive, I'm often punished by I'm often punished by fellow integration people. They don't like me to say this, but the truth is, you see, that the methods used by the ancients, going back, as Professor Agarwal says, going back to Vedic times, that method is still there. Now, in fact, if we look forward, the thing didn't end there. The problems of integration were the difficulties with this definition of integration were evident, and people continue to work on it. And we have Riemann's approach, then the theory of Lebesgue integral, which solved other problems. And then going down into the 1950s, you had a new version of this thing, which simply developed the theory of Riemann. And okay, I should say something about this. Well, maybe, in fact, if I go forward a little bit, some diagrams which this is particularly connected to the problem that Feynman had in doing his Feynman integral. This kind of function, how do you integrate it? Well, you can certainly integrate this between 0 and 1, or between 0 and 10, or up to any finite upper limit. For instance, the integral of Riemann. If we know that if an integrand is a continuous function, and if it's bounded, and if the domain of integration is finite, let's say from 0 to 3, for instance, that's integrable. We may not be able to find an antiderivative for the function, but we do know that the integral exists. Okay. However, if the upper limit is plus infinity, for instance, if we want to integrate this function from 0 to plus infinity, or from minus infinity to plus infinity, cannot do it by the methods of Leibniz or Newton. We cannot do it by the method of Riemann. We cannot do it by the method of Lebesgue. But the truth is that it has been it is a familiar integral, and people knew how to deal with it. But to deal with it, the best way of dealing with it is with the integral of Henstock or Kurzweil. Okay, so that's the kind of clue to this. Now, if we take we'll take a quick look, I think, at how Feynman approached this. Here is his integrand. We take the exponential of that, and we try to integrate it with respect to trajectories. Now, the problem with this is that there are xt, there are infinitely many variables here. If it was just x1 and x by itself, and we had this function of x1, then that's okay. We know what that means. It's like integral of y squared dy, something like that. If there were just two, this variable, there were two variables there, like if it was a compound variable x1, x2, and dx1, dx2, then this is okay too, you see. If here it's a function of x1 and x2. This is a function of two variables. It's an integral in the plane, and we can certainly do that. However, if there are infinitely many possible variables here, that's a problem, you see. But what Feynman did was he took a sequence of the variables, x1, x2, x3, like that. He integrate over any finite number of them into one dimension first, then x1, x2 in 2 dimensions, do it in 2 dimensions, then do it in 3 dimensions, do it in n dimensions. What you get then is a series of finite dimensional integrals, and then you take the limit as n to infinity of that, and he takes that as the meaning of the Feynman integral. Okay, I will have to, I think, quickly maybe draw it to a conclusion. The idea of the Riemann integral is that you partition the domain of integration, let's say from 0 to 1, and instead of letting the width of the integral be less than a constant function delta, we let it be less than the width of function delta x, where x is the point at which the integrand is evaluated. Now that is the generalized Riemann integral or gauge integral. That's in 1 dimension. We can do it in 2 dimensions. In this case, you see, we have, let's see, we partition the domain of integration by means of rectangles, okay? So we fill up the whole space with rectangles. Now each rectangle, let's see if I can, I've got to learn how to do this. So we have a point in the rectangle x, okay? And the rectangle is I1 cross I2, with I1 times I2, okay? Now, x, of course, in 2 dimensions is x1, x2, okay? So the generalized Riemann integral in 2 dimensions, we require that each, let me see, we require that each partitioning element of the domain of integration satisfy a condition like this, that the edge I1 should be less than the value of the function delta x1, okay, where x is the point at which the function is evaluated, the integrand is evaluated. So that holds for each of the partitioning rectangles in the domain of integration. Now that gives you a generalized Riemann integral in 2 dimensions. Okay, so I've now got to escape out of this. Okay, we can do it in 3 dimensions, like that. Now that's similar. We see we have again, the domain in 3 dimensions is partitioned by volumes like this. They're not squares, they're cubes. I mean, they're whatever the word is for these geometric figures. So x is a value inside that box. It has edges. It has 3 components: x1, x2, x3. The edges are I1 cross I2 cross I3. Now, each edge is restricted to be of length less than delta x1, or delta x2, or delta x3 in each case. Now, that's the condition which the integrand must satisfy in order to form the Riemann sum for the Riemann approximation to the integral. And again, provided that the Riemann sums satisfy a condition like this, then this value alpha will be the integral of the function in the 3-dimensional domain. Now we have to take this into infinitely many dimensions. Yes. So we don't have just a trajectory for the particle. Okay, let me write this down here as what this is. T. This trajectory is looks like this as a graph of position with respect to time. Okay, so in a sense, each time t, such as t1, it has a component xt1. At xt2, it is a component xt2. At time t3, yes,
Hello,
sir.
Your PPT cannot mute properly.
Okay, I better I'll click this off. This is lack of experience with the lack of experience with the system. So I apologize for that.
You have to.
I quickly go to try to give a solution to the problem of that Feynman had in his letter to me and in his paper, and how do we define the integral with respect to the trajectory? What we have to do is instead of this displacement time, this displacement graph of the trajectory, we have to convert the trajectory like this, like that kind of a graph, into a point. So in here, in the middle of this, here is a domain with 3 dimensions, and then with 4 dimensions, 5 dimensions, 6 dimensions. We can't really visualize this. We have infinitely many dimensions here, uncountably infinitely many dimensions. We can only realistically display 3 dimensions. So I display 3 dimensions. We have to try to imagine that there are infinitely many more dimensions to this box. Okay. If I look at the edges of the box, we have the point of evaluation is x, is inside that box. The function to be integrated is a function of that. It is the harmonic function that Feynman presented to us and that we looked at, e to the power of I over h times, etc. That's the integrand. That has to be integrated with respect to the variables. Now these are x1, x2, x3, x everywhere, you see. We apply the same reasoning to this, that in each dimension t1, that the edge of the box has to be less than delta of x1, the component of x in that particular dimension, and the same for each other dimension, like xt, for instance, and so on. So I can't write on this. I've discovered now that you can't see it, but that essentially, very briefly, is the solution presented in this book, the problem of defining the Feynman integral. That's the first problem. The second problem, you see, is how can we justify the exchanging the two operations, integration and summation to infinity. Now, the thing about it is that in this generalized Riemann theory, we do have suitable conditions which tell you when it is justifiable to exchange the operations, two limiting operations like integration, sum to infinity, integration and differentiation, and so on. All those things which you need for this subject if you wish to give a mathematical justification for the calculations involved. So I should not sort of continue too much longer. Okay, in fact, there's a little summary here, in fact, of that. What I claim to present in this then is a workable definition of the Feynman path integral, and secondly, workable conditions justify exchanging the operations of integration and summation to infinity. Why do you want to do that? Because these extremely useful Feynman diagrams, which are used in order to explain the interaction of particles in physical processes, such as, let's say, semiconductors or collisions or all the other things where this electronic and subatomic processes are interaction processes are taking place. Feynman diagrams, it seems, are extremely important there as a method of understanding ours. So here is a summary of what we're talking about. We have the classical theory and we have the quantum theory. We have Mr. Bader, that's Feynman's teacher in high school, who presented the least action principle least action principle comes from developments in classical mechanics through the 18th and 19th centuries, which go beyond the basic Newton ideas. And here we have the two things which I talked about to justify, to give a mathematical basis for issues in Feynman path integrals. And here we have the sources which I've referred to, and I think, in fact, I should stop there. I should really thank you for giving me the opportunity to come here and to apologize for not being too familiar with this online system of giving talks, and to express again appreciation of the opportunity to hear Professor Agarwal's lecture, and in fact to exchange a little conversation with Professor Ganguly again. So thank you so much for this. I should stop here, and I think I should mute my. Should I mute the system or something? How do I do that?
Hello, Sujay.
I should mute the.
In your chat box. Sujay.
Yes. Yes, sir.
Any question?
Sujoy.
Sujoy, please, Sujoy, ask some selected question.
Good evening, sir. One question from Vishu Raghav, that is it true that our observation of phenomena affects the phenomena of quantum physics?
Okay, am I back? Well, in actual fact, I have to say that I did say at the very start that I can't speak with any authority on physics. I do know, I have experience a little bit in a particular branch of mathematics, a particular branch of the theory of integration, and that's really all I can claim to talk about. But the question is quite interesting because I did have to read into why Feynman was saying what he said, what his theory was. I'd have to say, your question about observation, I found the best explanation of that in this, and it's not mysterious or mystical. It's quite practical. I think it's why people. Feynman is not a celebrity, not like Einstein. He's a little bit of a cult figure, I'd say. And some people are over enthusiastic about Feynman. But at the same time, I have to say that Feynman's explanation of that particular thing, as you can see it in this book, this is quantum mechanics. It's pretty well early on in the book, and it gives a physical. It's a little like the rubber ring in the cup of icy water. You see, it's not so simple as that. It's a real physics explanation of what's going on there, and it's not at all mysterious. It's not like the Schrödinger cat thing, the paradoxical stuff. It came across to me as not paradoxical. Now, I should stop there because I don't want to say things about physics that I'm not qualified to say. All I can say is that I've read stuff. I've read about Schrödinger's cat. I've read about all that stuff, the paradox, and other things of that nature. What can I say? I mean, I couldn't claim any authority in it, but I have to say I found Feynman's physics explanations rather clear. Do you know what I mean? I've also heard people say that or read that it can be that Feynman was such an expert at explaining that yes, he explained it, but when you were reading it, yes, I can see that. I understand that now. But when you went, well, maybe you didn't understand it so well. After all, it's still a bit of a mystery. So this is just my report of a member of the public, really, on issues in regard to physics and issues in regard to Feynman's version explanations of physics. They say, in particular, for instance, that the Feynman's 3 volumes of lectures on physics, and I've read some of them. I've looked them up to try to understand certain things, that kind of thing. Yes, they're very good. Maybe they're too good. I don't know. I mean, I wouldn't want to comment on that. But the original question, yes, about that, I would certainly recommend it to anybody. To look through. Which I can't find the page just now. It's too quick. But I would say yes. It's certainly worth looking at. So thanks.
Yes. Next question.
Thank you, sir. Thank you very much, sir.
Another question?
Sir, next question is, how do we bring the Feynman diagrams into school mathematics?
I think to answer the question, again, that's a physics question, and I have no authority there. It's also a teaching question. I've never taught physics. I've certainly taught some mathematics. This is true, but could you do it? Could you bring Feynman diagrams into school mathematics? Probably yes. You could do into physics, into the higher level high school physics course. I think you could. could it be done? Well, obviously, I think I have to think about a little bit about this in preparing the talk. How am I going to distinguish between classical physics and quantum interactions, which are quite different. They have this kind of explosive character. In fact, I thought about this one, you see. In classical physics, you have the idea of force. We have force equals mass times acceleration. That's certainly in the school program for physics, I'm sure. It still is. Certainly was 60 years ago when I was studying it. Now, one of the first things that this idea is used in historically, I think it was used to explain planetary orbits. Why do planets move the way they do, and all that sort of thing. Well, you see, they say that there's a force, a gravitational force, which connects a material object with another material object, like the sun. You got the Earth and the sun, and so on like that. So, that causes them to move in the orbit that they do. And you can kind of explain that, you see, with if you tie a string to a ball, you see, and start swinging it. Well, then you're the sun, the ball is the planet, and it goes round in a circle. Why? Because you have a string connecting the one body to the other body, you see. Well, then we say, well, of course, we know there's no string that connects Earth to the sun. What we say is that there's a force that connects the Earth to the sun. But what is a force? You say it's a silly question. Everyone knows a force is a force. You know, well, what is it? It's not. Is it a string? Is it like a string, or what is it? Is it there? Is there something in between the two objects, or what? You can say it's a stupid question, a childish question. But any question can be asked, and it can be childish or not, you see. But you see, this is the question of action at a distance, you see. Is there such a thing? I mean, outside my room here, you know, where I'm connected to the internet and all that, there's objects out there. Can I act on them at a distance? Maybe yes, maybe no. Have I got a string to join to them? At the moment, no, I don't. I can't act on it, you see. Okay, these are debating points in a way. But you see, we now come to the idea of quantum mechanics, you see, which has a rather different... Now, the idea of force is still present, I think, as far as I understand it. And again, please be cautious about anything I say about physics, because I don't claim to know anything about it. But force is present in quantum mechanics, but it's present in a somewhat different way. Now, if I take, here's an object, okay? It's stationary at the moment like this, you see? Now, there's a great mass underneath it, namely the ground, the earth, you see? And I can release this object. It moves, you see? Why does it move? Well, the force of gravity pulls it towards the earth, you see? But now, I don't know if there is a quantum mechanical theory of gravity. If there is, I think there is something that, well, what they may say is, again, I'm sure there are people in the audience who know infinitely more about this than I do, but you might say that what's happening here is not that a force pulls the one object to the other, but that what happens is that there is a particle exchange between the two objects, which has an effect on the motion of each object, but particularly on this very small object. The other big object is not affected very much, but there like a bullet is fired between the two. So it's not that there's a string here, but there's a passage of a particle or particles between the two, and that has an effect on the motion of each. We saw how one electron approaching another one, they don't see each other initially, but then something happens, an explosion takes place, a photon is exchanged, and then they start to move in different directions, you see. So in the case of gravity, you could say that maybe there is a particle exchange. I think the particle is called a graviton or something like that. I think in the previous lecture, this was mentioned, or in one of the questions. Yeah, in the lecture, I think Professor Agarwal mentioned this. Can you bring in Feynman diagram? I think you could bring in a simple Feynman diagram if you wanted to say that the idea of physics has changed a little bit from pre-20th century to post-20th century. Well, yes, these very simple Feynman diagrams, which are really a great simplification, to be honest. That'll be clear if you read the write-up particularly in these physics books. Not so much in my book. I'm selecting out mathematical conundrums or problems in this theory to try to give an explanation in modern mathematical or integration terms where we can make a contribution which makes some of these arguments perhaps more mathematical. Let's say, put it like that. I don't know what the correct word is here. So yes, I think maybe it's possible for a good teacher to bring in some of these more modern quantum mechanical theories into the classical explanation of physical phenomena. So that's all I can say.
You have another question. So,
sir, Anguli sir. Hello, sir. You are finished this lecture. Please tell.
No, Sujay, have any other question?
No question.
Okay.
Already
okay.
time.
Muldowney.
No, sir. It is okay, sir.
Just. Sujay have no question. Now back to Muldowney. Muldowney.
Yeah, well, I think I've completed the lecture and tried to answer some of the questions. So again, I have to thank you, Professor Ganguly, for your, and the conveners and the audience for listening to me. Thank you very much.
Duties, this contribution for this world. Okay, the Feynman also this only one field. I am talking about a field state. Muldowney?
Professor Ganguly, the sound is now very bad. So if I understand you, only caught a little piece of what you said is to do with the award of Nobel Prize for work in this area. Now, Feynman certainly got the Nobel Prize in 1962 for his theory of quantum electrodynamics, which is an explanation of the phenomena of light. Now, I mean, light has been explained in physics terms. I'm not sure about the history of it, but certainly by the 19th century, you had electromagnetic waves and so on. Now, they belong to classical mechanics as far as I understand it, but Feynman brought this, the theory of light, it really does belong in the class of quantum mechanical phenomena. He was, of course, many people contributed to the development of that theory, for which he was awarded the Nobel Prize in 1962.
Okay. Feynman is same as the Feynman integral, say what's the path integral?
I'm sorry, the Feynman integral
is same as the path integral.
Oh yes, of course. I am so sorry. Yes, the path integral is just another word for Feynman integral. I'm sorry. I can see that I may have misled you there on that. When you say the Feynman integral or the path integral, the Feynman integral is a little bit more accurate. The word path integral is sometimes used in other connections, but most people, I think, will if you say path integral, usually they'll think of Feynman integral. So they're not quite there is another use for the expression path integral in my experience, but they're basically the same.
Thanks to Professor Muldowney.
Thank you.
And very lecture. I think everybody will be benefited by this lecture. Thanks again, Professor Muldowney, and also Professor Agarwal for delivering their nice lecture in seminar. Omanjan.
Okay.
Now this is a time for conclude the webinar. I am requesting Professor Prabhujan Kumar Rana to give vote of thanks and conclude the webinar. Rana sir.
I am very much thankful to our principal for continuous support and advices, which has greatly helped towards the successful international webinar. I sincerely thank the members of the advisory committee for their valuable suggestions. Again, I would thank Professor Ravi P. Agarwal and Professor Pat Muldowney, who took their time of their busy schedule and showered us with their pearls of wisdom and knowledge. We are truly humbled by their presence. Thanking you once again. I am thankful to all the participants. I am pretty sure that the participant must have benefited by attending the webinar. And thanks for all. Thank you.